Okay, we're going to keep looking at trig, and today we're going to look at special triangles and the cast rule. But first, we need to keep talking about reference angles. So something that we haven't really properly discussed yet, but I bet you figured out, is this reference angle situation. So let's say we have an angle that's 45 degrees drawn in standard position. Okay, so right here. This has a reference angle of 45 degrees. Okay, and the angle itself is 45 degrees. Okay, now over here in quadrant 2, we can have another reference angle of 45 degrees. And this is going to be an angle of, 45 less than 180 is 135. So this is a 135 degree angle. And it has reference angle 45. Down here in quadrant 3, we can draw another angle with a reference angle of 45. And it's going to be 45 above 180, right? So what is this going to be? This is going to be a 215 degree angle. Okay. And then finally over here in quadrant 4, there's yet one more angle that also has a reference angle of 45. Okay. And that angle is 45 less than 360. So this is going to be 315. Now, these angles all share a reference angle. So 45, 135, and 215, and 315. Good gracious, that's 225, isn't it? Maybe one of these days I'll learn how to add. 225, okay? And 315, they're all associated together because they have a reference angle of 45. That means if I go and draw triangles underneath them, they will all have very similar behavior. It also means that their sines and cosines are going to be related. Now, 45 is a big deal. 45 is one of our special angles, okay? Can you guess what the other special angles are? You got it. It's 30 and 60. So same deal with those. Let's look at 30 for just a second. If we look at a graph with a reference angle again, oops, that's not where 30 is. 30 is way down here. 30, that's a reference angle of 30. Now a reference angle of 30 in quadrant 2 is going to be what? It's going to be 150 degrees, right? Because there's a reference angle of 30 right here. And a reference angle in quadrant 3 is going to be 210 degrees, right? See my 30 degree reference angle? And then over here, my 30 degree reference angle is going to give me an angle in standard position at 330. So same deal. This 150, 210, 30, and 330 are all associated together because they share a reference angle of 30, and 30 is a special angle. Now, the final one is 60 degrees. So 60 degrees is a similar situation. We're going to go through the same process. Here's my angle in standard form at 60. Right? 60 degrees is my reference angle, so 60 degrees in quadrant 1. In quadrant 2, a 60 degree reference angle is going to be an angle at 120, right? 60 degree reference angle. A 60 degree reference angle in quadrant 3 is going to be 60 past 180, so that's going to be at 240. And then in quadrant 4, Here's my 60-degree reference angle again. This is going to be at 300. So these are all associated angles for 60 degrees. They're a big deal, and they're just worth noting and pointing out right now. So 60, 120, 240, and 300 are all going to share the same characteristics that are similar, I guess. I don't know if that's the right word. And it all has to do with a common reference angle. Okay, so let's push this a little bit further. So 45, 30, and 60. These are the big dogs. These are what we call special angles, and special angles lead to special triangles. Okay, don't these all work themselves really nicely with triangles? So let's talk about 45. If we have a 45-degree right triangle, then all the angles are going to be 45 degrees. Now 30 and 60 is a little bit different. 60 degrees lends itself to an equilateral triangle, right? All the sides are the same. These are all 60, 60, and 60. So we're going to manipulate these triangles and turn them into what we're going to call and refer to our special triangles. Let's start with 45. So a 45, 45, 90 triangle is a right triangle that looks like this. Okay, right triangle. 45 degrees. We say in math that we want this to be 1. Okay, this is going to be automatically given a length of 1. If this has a length of 1, then this side also has a length of 1 because it's a 45-degree triangle. Therefore, we want to know this side. So if I use Pythagorean theorem, I get 1 squared plus 1 squared equals c squared. So 1 squared plus 1 squared is 2 equals c squared. So therefore, the square root of 2 is c. So this is the square root of 2. This ratio is a special triangle, okay? This ratio. I'm going to rewrite that so you can see it this way, root 2. So any triangle, no matter how big or small on the whole planet, is going to have this ratio. So let's say I want to double that. Let's say I want to make this bigger. Let's say I want to double the whole thing. If I want to make it bigger, I know that's not actually bigger, then I would double everything. So I would have 2 root 2. And then I would have 2 times 1 and 2 times 1. What if I wanted to triple it? If I wanted an even bigger triangle, I would have 3 root 2 and 3 times 1 and 3 times 1. Okay, so that ratio never goes away if you've got a 45-degree triangle. Now here's the kicker. This can all be applied to the graphs we've been drawing. Okay, so follow me. Here's my graph. Okay, and if I draw a 45-degree angle right here, okay, here's my angle in standard position. This is 45 degrees. I know that the ratio of any triangle that's formed in here, okay, any triangle formed in here, has to have a 1 to 1 to root 2 ratio. Okay? That means if I want to know the sine of 45, I know that sine is opposite over hypotenuse, and I know that opposite is now considered y, and I know that hypotenuse is now considered radius, right? So that means right here I've got 1 over root 2. So the sine of 45 is 1 over root 2. Okay? Now, if I go draw that same reference angle at 135, it's going to still have that same triangle underneath here, right? That's got that same ratio of 1 to 1 to root 2, which means the sine, oh, sorry, what's the difference here? This is -1, right? So that means the sine of 135 is also going to be 1 over root 2. Go ahead, go put it in your calculator. Go put in your calculator sine 45. I bet you get 0.7. Then do the same thing. Put in sine of 135 in your calculator. What are you going to get? You're going to get 0.7. Now, take this. Take 1 divided by root 2. Put that in your calculator. Tell me what you get. Oh, I bet you got 0.7. They're all the same. And the reason they're the same is because of this reference angle that is shared, and because of the ratio of any triangle you draw underneath that angle will all have the same sides. Now, it's going to get a little more fun when we come down here to quadrant 3. Let's come down to quadrant 3, and let's draw, I need a new color. Let's draw our same angle down here. Okay, so what do we say we have down here? 225. Why do I always mess that one up? Okay, so here's my triangle this time. This time I have -1 as my y, and I still have my root 2. So my sine of 225 is going to be -1 over root 2. And I know that because I know in quadrant 3 my y value is going to be negative. Like, that's just something that's embedded in our understanding. So, same deal. What happens if you put in the sine of 225? What do you get? Oh, guess what you get? That's right. -0.7 if you plug that in your calculator. But the exact answer is 1 divided by root 2. That's the ratio. All right? So, keep going. It's going to be the same situation over in quadrant 4. All right, so that's how special triangles for 45 degrees work. They're really important. They're extremely useful. Let me just recap where I got this. I, for reasons we'll get to later, picked 1 as the side length. I picked 1 originally on my 45-degree triangle because it's easy to turn in, like it's just like a nice number to reference. If this side is 1, then this side has to be 1 because it's a 45-degree triangle, and they all have the sides have to match. Based on that, the hypotenuse has to be root 2. That means this ratio has to occur in any size triangle. Therefore, we kind of applied that to quadrant 1, quadrant 2, quadrant 3, and then we could in quadrant 4, we just hadn't gotten there. And we were able to see that the sine of all 4 of these angles is the same. It changes from positive to negative depending on what quadrant it's in. Okay? If I kept going here, I guess I can do that for you. If I kept going, let me find one more decent color that's not terrible. Okay, if I kept going and did quadrant 4, do you remember what the angle is with the reference of 45? It's going to be 315. Is that right? Yeah, 315. Okay, so under here, my triangle now is 1, -1, root 2. So that means the sine of 315 is going to be -1 over root 2. Okay, so I got a negative again here. Now, that brings up the cast rule. Are you ready for this thing? Actually, I changed my mind. We're not going to bring up the cast rule yet, but this is what special triangles look like for 45, 45, 90. Now, we're going to do this again with 30 and 60, and they go together. But for now, let's leave it at this. So let's do a couple of practice problems of what we can do based on this information. Okay, what if I ask for you to find for me the exact value, okay, so exact value of cosine of 135, okay? So that means you are going to figure out what quadrant, okay? So first of all, you're going to say, what quadrant is this in? What quadrant? Do you know? Okay, quadrant 2. Okay, so that means you know that in quadrant 2, you've got a negative x and a positive y. So you've got something that looks like this. And we know we have 1, 1, and root 2. Cosine requires adjacent over hypotenuse. So your adjacent is negative 1 over root 2. That's all you're going to do. What if I ask you to find for me the tangent of 45? The exact tangent of 45. You ask yourself what quadrant. It's in quadrant 1, which means you've got 2 positive values, right? You have a positive x in quadrant 1 and a positive y. So here's 45. Again, 1, 1, and root 2. Tangent is opposite over adjacent. So you're going to say opposite is 1, adjacent is 1. The exact value of the tangent of 45 is 1. All right, makes sense. I hope that works for you.